But let's suppose you asked a little kid who's very, very bright, but ignorant. Never seen it before. You say, kid, I'm going to drop these two objects. You tell me which one hits the ground first. I'll give you a Hershey bar. Kid says, with almonds? Yeah, with almonds too, all right? You tell me which one hit the ground first. And the kid says, well, can I feel those things first? You say, yeah. The kid take this. He says, that's a pretty heavy piece of metal there. It's aluminum, but there's enough of it, so it's kind of heavy. Big gravity force acting on that. Kid take this. Oh, this little tinky ball. See, it's not very heavy at all. It's very, very light. God, doesn't weigh anything. Come on, kid, which one hits the ground first? He says, well, obviously, the heavy metal going to hit the ground before this little red ball. You say, how come? God, what is more force acting on it? I know when I'm pulling my toys, if I pull with a big force, it got a big change in motion. If I pull with a little force, it only change a little bit. There's more force, more gravity force acting on this. Whip, boom, gonna hit the ground. Give me my Hershey bar. Then you take it and you drop these things. And the kid's like, they fell together. Kid doesn't get the Hershey bar. You know what that kid is saying? That kid is saying this, that the acceleration, change in motion, is directly proportional to the force. I got a question for you. Is that kid correct or incorrect? Incorrect. Begin with a C. He's correct. His thinking is fine. But you know what? The experiment doesn't line up with his thinking. One of the beauties of science, we can experiment to see if our thinking is complete. Let's suppose you ask some other kid. They live in a different part of the island. You ask the kid the same question. Hey, kid, which one going to hit the ground first? The little dinky ball or the heavy weight, huh? And the kid say, can I feel him? And this kid thinks differently somehow. Instead of judging how heavy, what the kid does, he goes like this. Wow, it's pretty hard to change the state of motion of that. Got a lot of resistance to change. Kid takes this. Oh, this little thing here. My gosh, easy to change the state of motion of that. This doesn't have as very much mass. This has a lot more mass. Yeah. This has a lot more inertia. Yeah. Come on, kid. Which one hit the ground first? He says, well, this thing here got so much inertia that, of course, the little red ball going to hit first. He said, the red ball hit first? Yeah. By the time this thing gets around to responding to gravity, whoop, this thing will be already down there. Because I know when I'm pulling things, I'll pull something very light. It, boom, pull something heavy, it lags behind. This thing is going to lag behind. So the kid says the little ball wins. So you drop the two things, the beauty of the experiment. Whoop, the kid. What's wrong? You know what that kid's saying? Is that kid saying something like this? On your toes. Is that kid saying the acceleration is proportional to the amount of mass? Check your neighbor. First of all, I got to ask you guys all a question. Which number is bigger? How many say, oh, obviously this number is bigger? Show of hands. Get out of here. Get out. Out. No, this is the bigger number, right? Okay? So it turns out that, hey, as the mass gets bigger and bigger, what's the acceleration get? Less and less. So it's this way. This is called an inverse relationship. Make something big, this gets small. Make this small, this gets big. It's upside down. It's inverse. So what the kid is saying is, the more massive, the less the acceleration. See, if I wrote it like this, now the kid is saying, the more massive, the more it will accelerate. No. He's not saying that. He's saying the opposite. He's saying the inverse. He's saying this. But you know what? He's incomplete. And this kid, incomplete. Now get these kids together. Get them together, and you talk about some nice physics. Because when you get them together, what do you got? You got what Newton got. You got this right here. Yes, the force. Yes, the inverse mass. Here's the whole thing right there. Yay. Let me show you what I mean. Here's the force acting on this. Here's the force acting on this. Looks like this one's going to be winning, huh, gang? Let me caution you on something. Whenever I ask you to compare the accelerations of different things, acceleration, don't shoot from the hip. Use a crutch. And that crutch is Newton's second law. When I say which of these accelerates more, It's another way of saying which goes faster, which gets down to the ground first, huh? Which accelerates more? Use the equation to guide your thinking. Because the acceleration depends not only on the force, but on the what? And what's the mass of this thing, gang? The mass of this thing here is like this. What's the mass of this little dinky thing here? Almost nothing. It's got a mass like this. So are the masses the same? Are the forces the same? Are the ratios of force to mass the same? Do you see that's different? The ratio of both are the same. And that ratio is the acceleration.